Okay, welcome to this video for Chem 161, looking at some additional Chapter 3 content on the de Broglie relation. And applying it to the idea of electrons as waves. So in the de Broglie relation, we have the important idea that the wavelength can be calculated and is from the mass of the object and its speed, and is further quantified by Planck's constant. So de Broglie helped us rationalize that wavelength of any object is inversely proportional to momentum of that particle. And so this is captured through his equation, which basically shows us that the wavelength is equal to h, which represents Planck's constant, divided through by momentum, which of course is simply the mass times the velocity. So be very careful there. That's a v for speed or velocity, not what we've seen before for frequency. Okay. So we have here Planck's constant. Okay, and we'll typically see this applied in many quantum mechanical equations and other equations that relate particles and electrons to energy levels. So we'll see this constant a lot. And it is 6.626 times 10 to the minus 34 joule seconds. Notice it's a product, joule seconds. Okay, and we saw that the wavelength in many of these equations is output in meters. So we'll put some comments here below this equation. So the units here will be meters for wavelength. We have the constant units already listed over here. And so that is, we expect H to have units in the form of joule seconds. And the mass here must be in kilograms to use this equation, and speed must be in meters per second. Okay, so when we do all this, we will end up leaving behind meters, and which is appropriate for the for using this equation. In case you want to kind of see that better, you can see that the joule here is equal to 1 kilogram. So 1 joule is equal to 1 kilogram meter squared per second squared. And that'll allow you to cancel all but a meter and leave behind the units for the wavelength. Okay, so this equation is powerful. It tells us that we have an inverse relationship between any particle's wavelength and the momentum, which is of course mass times speed. So you traveling with some speed have mass and velocity. You traveling at some speed have a wavelength. A baseball thrown by a pitcher at a catcher's mitt has speed. That mass is lighter, and so we start to see a little bit of a longer wavelength than you, given that you are heavier than a baseball. And it's not until we get to very light objects that we see wavelengths having appreciable distance that we might expect that's on the order of that we've seen before for waves associated with the electromagnetic spectrum coming from example from the sun. Okay, so let's take a look at an example here. The example might say, calculate the de Broglie wavelength okay, we'll say in meters of a 142 gram baseball thrown at 44 meters per second, which is close to 100 miles per hour, typical of pitch in the big leagues. Okay, so we have the equation above. We're given the mass of the baseball in grams, and we're given the speed of the baseball in meters per second. And so we have to do a little bit of work to better ready the mass information here to use our de Broglie relationship. So as we saw before, mass has to be in kilograms. So we're going to take the 142 grams and first convert this into kilograms. So 1 kilogram is 1,000 grams, and this is going to give us the mass as 0.142 kilograms. Better ready for the equation above. Okay. So with that, I think we can use the equation now. Lambda, expecting an answer in meters, is equal to Planck's constant, 6.626 times 10 to the minus 34 joule seconds, divided through by the mass in kilograms. So this is 0.142 kilograms, times the speed in meters per second. That's a key requirement. Can't use any other speed variations there. And so this is the 44 meters per second. And with those units correctly applied to the equation, we can rely on the joules canceling and leaving behind just meters for our answer. And so this would give us an answer of 1.06 times 10 to the minus 34 meters. Okay, so clearly a baseball being thrown here, the wavelength of this baseball, right, from the same feature to the same feature on the wave pattern, is very short, 10 to the minus 34 meters. And a baseball, this is about as fast as a baseball can travel, and it's still barely showing wave-like characteristics at 100 miles per hour. And so it's not until we look at very, very light objects, like we know the properties of the electron to be very light, that we start to see wavelengths that are more in line with what we might expect. So this helps us understand why there might be wave-like properties for the electron, as we'll see in a later video. And it brings us to the topic of a standing wave that we're going to use to apply to our model for the atom. So we'll kind of fast forward down here and think about the goal of trying to explain how a standing wave representing the electron around the nucleus might better explain what some flaws in the planetary model of the atom. So if you recall the planetary model of the atom, we had a nucleus and we had orbits where electrons could reside, and etc. Now, one problem with the planetary model that isn't explained by sort of particle type physics and particle models for electrons is that each of these electrons is negative in charge, and the nucleus is very much positive in charge. So unlike the moon and the Earth, we have electrostatic attraction here between the electrons and the nucleus, and the electrons should fall towards that nucleus, given the opposites attract rule. And in doing so, they would radiate energy and the atom would collapse. And so clearly this isn't what happens, and this is one of the major flaws in the planetary model for the atom. And we need something to explain what holds the electrons at a given orbit, if you want. And that's where the wave-like properties of the electron come into play. So from the de Broglie relation, we know that these electrons are very light, to the point where a model for their wavelength will work. And so we'll see wave-like characteristics dominating here. And we'll see that the electron can be modeled as a standing wave, and that standing wave can only sort of repeat back onto itself. That is, start right where it ended in a wave pattern around the nucleus if we have a standing wave pattern. So to rationalize this, we'll look at an example which is a violin, and the chords on a violin can be thought of as a nice stretched linear version of a piece of matter that can show a standing wave. So plucked the right way, we would see half a wavelength in that pattern. Remember that to show the full wavelength, we would have to return this all the way back down. Plucked a different way, or if there's more tension on a violin string, we might see a full wavelength, so that is 2 half wavelengths from sort of the anchor point to another anchor point on the violin, and so forth. So we can get different sort of standing waves in here, where from one anchor point to another, the wave pattern may not move, but simply stand in place. Okay, and so we typically see standing wave patterns when there is an integral repeat, that is an integer, for the number of wavelengths between those anchor points. Okay, so here we can see 2 half wavelengths would allow this crest to simply move straight up and become the peak, and this peak to fall straight down and become the well, and that standing wave would not have its features move laterally on the violin. And so these standing wave patterns can be seen in a lot of string musical instruments, or even rope tethered to a wall and kind of shook the right way with the right amount of tension in that rope. If you imagine now that rope or the violin string wound around a circular feature or disc, we can imagine these standing waves locating nicely around some central object, like, for example, a nucleus in an atom. And so this is the rationale to applying the wave-like characteristics and standing waves for electrons to explain why certain orbits are allowed, if we're hanging on to any ideas from the previous planetary model, and why the electron can't simply shift to lower and lower and lower orbit distance and fall into the nucleus. A standing wave would keep it at some distance, if you want, from the nucleus. And so this was some of the history and some of the earlier rationalizations for explaining how electrons are not only understood to be waves from physical models like the de Broglie relation, but also applying them to fit according to some circumference around the nucleus. And so when the circumference isn't just right, you can see here that the beginning of the wave does not match up with the end of the wave the way we want it. And so this orbit would not be allowed and wouldn't be a good fit for a standing wave electron around an atom in this sort of hybrid wave quantum planetary model for the atom. Okay, so those are some of the ideas highlighted in your chapter to show that there's things explained better by wave-like characteristics for electrons.